Compiler design, basic blocks and flow graph, DAG representations of basic blocks. Coming to basic blocks. A basic block is a sequence of consecutive statements in which flow of control enters at the beginning and leaves at the end without halt or possibility of branching except at the end. For example, if you take T1 as A into A, T2 equal to A into B, so T3 is dependent variable on T2 and T4 is dependent variable on T3 and T1, and T5 it is calculated B into B. T6 is equal to T4 plus T5. So for this program code, we are defining basic blocks. How to define the algorithm for construction of basic blocks? So we call it as partitions into basic blocks. So the input is, it contains the sequence of 3 address statements. Output is, it contains a list of basic blocks with each 3 address statement in exactly one block. Method. First, identify the leader in code. The rules for identifying leader are as follows. The first statement in 3 address code is a leader, and second one, any statement that is the target of a conditional, unconditional jump is a leader. Any statement that immediately follows a conditional or unconditional jump is a leader. For each leader, its basic block consists of the leader and all statements up to but not including the next leader or end of the intermediate program. For example, if you take a program code, that is, we are defining product as 0, I is equal to 1. So we are defining the loop, that is, in the loop, product equal to product plus AI into BI. So we are calculating the multiplication of two variables, array variables, and store that value into product. Then increment I value while I is equal to 0. That means the loop continues from 1 to 10. So the procedure we are storing into prod variable. So coming to the from source code to 3 address code, we are converting the source code into 3 address code. Prod equal to 0, I is equal to 1, T1 is equal to 4i, T2 is equal to A of T1. That means the T1 value is the index value for array A. T3 is equal to 4 into I. That means T1 and T3 are same value. And T4 is B of T3. That means the array B contains the T3 index. And T5 will calculate T2 and T4. Then T6 is equal to product plus T5. Prod is equal to T6. That means we are calculating T6 and then prod is equal to T6. T7 is equal to I plus T1. I is equal to T7. If I is less than or equal to 10, go to 3. That is from T1. This is the logic. We are converting source code to 3 address code. The example, from 3 address code, we are dividing this one into basic blocks. That is, initial block B1 is initial block, that is prod is equal to 0, I is equal to 1, and looping whatever the statements we are using in the loop, that is B2 block. This is another example. Consider that 3 address code to set a 10 by 10 matrix to an identity matrix. So this is a code. We are initializing I and j value. We are calculating t1 is equal to 10i, t2 is equal to t1 plus j, t3 is equal to 8 into t2, t4 is equal to t3 minus 88. So a of t4 initial value is 0. J is equal to j plus 1. If j is less than or equal to 10, go to 3. That means t1 is equal to 10 into I. This is internal loop, and whenever it completes, the I value will increase, and this is external loop. From here to here, this is external loop. Based on this, we are dividing the blocks, that is B1, that is I value, initial value, and B2, j is equal to 1, and B3, this is under the loop, and B4 is I is equal to I plus 1, that is increment of I value. That means it completes the j loop, and I is equal to 1, another block, and remaining all are B6. Coming to flow graph. Flow graph is a directed graph which gives the flow of control of information to the set of basic blocks making up a program. The nodes of the flow graph are the basic blocks. A control flow graph is used to depict that how the program controls is being passed among the blocks. It is useful in the loop optimization. This is an example of flow graph. For the vector dot product is given as follows. That is, block B1 contains initial values, and coming to block B2 is the procedure of the loop. And coming to flow graph, B1 flows from B2 and it iterates from 1 to 10. 10 times it can repeat. That means it shows the looping statement. Block B1 is the initial node. Block B2 immediately follows B1. So there is an edge from B1 to B2. The target of jump from last statement of B2 is the first statement of B2. So there is an edge from B2 to B2. B2 is a successor of B1 and B1 is the predecessor of B2. This is another example for converting basic blocks to flow graph. Coming to DAG representation of basic blocks. DAG means directed acyclic graph with no cycles. Useful data structure for implementing transformations on basic blocks. It gives a picture of how the value computed by a statement is used in subsequent statements. Constructing DAG from 3 address code is a good way of determining common sub-expressions. Nodes in DAG. A DAG for a basic block with nodes are labeled as: the leaves of graph are labeled by unique identifier, and that identifier can be variable names, or constants. Interior nodes of the graph is labeled by an operator symbol. Nodes are also given a sequence of identifier for labels to store the computed value. Coming to applications of DAG, DAGs are useful for removing common sub-expressions, renaming temporaries, finding names used inside the block but evaluated outside the block, finding statements in the block that could have their computed values used outside the blocks, statements that can be reordered or executed in parallel. Coming to DAG application, the input is basic block, output is label for each node. Label is an identifier for leaves. Label is an operator symbol for interior nodes. Each node has list of identifiers. Given a function node of identifier, it returns the node currently associated with the identifier. Statement type x is equal to y operator z. Second statement x is equal to operator y. Third statement x is equal to y. If node of y is undefined, then create a leaf labeled y, and this is now node of y in case of x is equal to y operator z. Do the same for z also. Determine if there is a node labeled operator with node of y and node of z as the left and right children in case of x is equal to y operator z. That means operator is the root node, y is the left child, and z is the right child. Determine whether there is a node labeled op, op means operator, whose lone child is node of y. Let n be node of y. For example, if you take an expression a plus b into a plus b plus c plus d can be converted to 3 address code follows as. So in this expression, a plus b first we treated as t1, and for t1 we multiplied b value, we named it as t2, and coming to t3 is equal to a plus result of t2, and coming to t4 t3 plus c, t5 is t4 plus d. So for this 3 address code we are constructing DAG graph. First step, we are constructing t for t1, that is plus is the operator, so we are initializing as root node, and a b are child node for t1. Next step, here for t2 b into t1, that is variable already we have, so we are connecting b for t2. For calculating t3, a plus t2, that means a value already we have, so a plus t2, then t3, t4 and t5. This is another example using arrays. So here t1 is 4 into I, that is the operator star mark and I value 4 we consider it as t1. And coming to t2, that is array we are calculating for t1 to a of 0. A of 0 means initial value 0. So array we are defining the operator. This is the continuous diagram.